ladies and gentlemen. A warm welcome to our LINXDays Southeast Asia 2021 live from Singapore. Thank you for taking your time to join us here today. For the benefits of those who are here for the first time, LINXDays is an annual event that connects with our existing and new clients from Southeast Asia to get to know us, as well as the updates of our latest products. After our last LINXDays webinar in June, we're excited to host another and a final one for this year. Today, we are thankful to have SPECIM to join us. With us, we will have two distinguished speakers, S.E.A. and S.E.A. from SPECIM in Finland, to share on what hyperspectral imaging has to offer for the various industries. Before we meet SPECIM, let's have the Managing Director and Head of Southeast Asia Sales Division from LINX Singapore, Mr. Henry Chia, to do an opening speech to grace the webinar. Let us welcome Henry.
Hello, good afternoon, everyone. I'm Henry from LINX Singapore, Managing Director. Welcome to LINXDays Southeast Asia 2021. We are so excited to see you here. Greetings to our partners from Oulu, Finland, and our beloved guests from Singapore, Malaysia, Thailand, and the rest of Southeast Asia. This is the last of our LINXDays Southeast Asia 2021. Today, we are very excited to talk about hyperspectral imaging, featuring the experts of SPECIM. We have talked much about 3D and machine learning previously. These are much used in electronic applications and semicon production. In the world now, we are very concerned about being green, environmentally friendly, and sustainable in our production processes. With COVID and health events disrupting our supply chain, we are now keenly focused on food supply and the stable production of food and drug medicine for our consumption. Just like Singapore's ambitious plan of being self-sufficiency in our food production by 2030. Our speakers from SPECIM are going to share with us their vast experience in this fastest growing imaging technology in spectral imaging. This technology is now being implemented in many important fields like food production, color measurement, pharmaceutical production, waste and recycling, vegetation and agriculture. This is advanced manufacturing we are talking about now. It's arriving into our backyards from Southeast Asia, and we hope our customers will be able to find strong technology to be able to tap onto these opportunities in many sectors. I hope through today's sharing, you'll be able to see how hyperspectral imaging is able to help you in your respective fields of business. Machine vision is now more about finding the shapes and sizes. Hyperspectral imaging now gives you the capability to extract much more data beyond the obvious and visible features. I hope you all will have a fruitful time today with our partners from SPECIM. Back to you, Cecilia.
Thank you, Henry. Thank you, Henry, for the opening speech. So now, in our next segment, we are pleased to welcome S.E.A. and S.E.A. who will be presenting the focus of today's webinar, the world of hyperspectral imaging. Over to you, S.E.A.
Thank you very much. I will now share my screen. Here, wait a second. Here, share my screen. Like this. So, hello everybody. I am Jussi Soukkamäki from SPECIM, and I work here as a sales and business development manager. And I thank LINX Singapore for this opportunity to come to this webinar to talk about hyperspectral imaging as a technology, and also our products and how to use those products in different applications. But before we go into the details of the technology and applications, I just would like to tell you a few words about SPECIM today. So SPECIM has founded already in 1995 by 3 men here at Oulu, Finland. And one of those men is actually Esko Herrala, who will follow me with the example of software application, how to actually apply the hyperspectral imaging today. Since 1995, we have delivered over 8,000 spectral cameras and spectrographs, and there is 70 people working in our company. Our sales has always been global. So we have sales offices at Barcelona, here at Spain, in New Jersey, here in USA, and in Shanghai, China. But in addition to our own sales offices, we have also worldwide distributor network, and Link Singapore today is one example of our distributors, and we work closely with them. Quite significant change in SPECIM's history has happened last year when actually Konica Minolta acquired SPECIM at the December 2020. Since that, we have been then part of Konica Minolta Group, and everything has went very well. Today, you can consider SPECIM as with many different numbers as a global leader in hyperspectral imaging, and the reasons behind that success is that we have all important functions in-house. So we have our R&D and production functions at the same building. So whenever we develop new products, those products are developed together with production. So because we are located at the same building, product developers and those who will manufacture actually those products, they are working together, and that way they can seamlessly develop products that can be then transformed easily to the production. And after those products have been developed and manufactured, we have also support function inside the company that helps our customers and salespersons to find right product for their applications. There are very wide variation of different applications where you can use hyperspectral imaging, and also SPECIM has very wide selection of different products, and it is important to understand what is the right product for your application. So for that purpose, we have a support team that helps our customers and salespersons to find the right product for their customers' applications. But in addition to that, we have also after-sales support that helps our customers to get instruments working as they should be. So we help customers to use the cameras so that they can get very good data and develop their own applications forward. So those are the key parameters, key things that are behind the success of SPECIM. And here, in a nutshell, the timeline of SPECIM. SPECIM history actually reflects the history of hyperspectral imaging, as SPECIM has been a pioneer in this market. So as the history of hyperspectral imaging starts from the airborne applications, also SPECIM history starts from S.E.A. series, so airborne cameras. And during the years, step by step, SPECIM has developed cameras that can be used in machine vision application and in industrial applications. And here, year 2017 has been very important year in the SPECIM history. That year, SPECIM launched the SPECIM FX series, that is a product series especially designed for industrial machine vision applications. At the same year, SPECIM launched IQ camera, that is fully portable hyperspectral imaging, first in the world, where you can use this camera similarly as you can use normal compact camera. And after that year, SPECIM has expanded FX series product family with the FX50 for the MB range. And also SPECIM has developed cameras for the drone applications, and SPECIM one concept for the industrial applications, so that industrial customers can take camera in use as easily as possible. So now let's start to think about what is spectral imaging. If you see this image here, with human eye, you can see different colors. The reason for that is that actually in human eye, there are 3 different cells that are sensitive for the different colors. So we have cells in the eye that are sensitive for the blue, green, and red light. And now when the light enters to our eye, different cells get a different amount of color, and that way actually we can see the color. So when this red color enters human eye, that cell that is sensitive for the red color will give a signal to our brain that now there's red color. And as a combination of these three colors, we can actually then show the other colors. But if you think about the industrial and machine vision, there is no human eye seeing these colors. But actually, then we have to create the sensors that are sensitive for the different colors. And then we are talking about spectral. So now, instead of only 3 different bands, we can actually create a sensor that can see hundreds of bands. And when we now measure these different colors, like this blue color here, you can see that the spectrum of the blue color looks like this. And if you look the spectrum of the red color here, you can see that it's a different. And this way, actually, now softwares, algorithms, and robots can differentiate between different colors as actually also with different materials. We call these curves here as a spectral fingerprint of different materials. Like we can see that here is a material that has red color. Here we have a material that has blue color. And when we compare these spectra from the different colors, we can see that they are different. And now those algorithms can understand this language. So now the question is, where comes the word imaging? And it comes when we combine the spectral fingerprints, spectral measurements with imaging. Then we are talking about spectral imaging. So actually now, because we have taken the image of this color image here, color picture here, we can locate the different color to this part. So blue color is here and red color is here. So we combine spatial information with spectral information, and that opens a lot of different applications. But how to benefit now this? So here is one example. So if you have, this is from the sorting industry. This example is coming from the sorting industry. So let's say that we have on the table different items that look similar for the human eye. And we should sort them like this so that we can say that what is PET, what is PVC, and so on. So the answer how to do this is spectral imaging. So now when we know that PET has this type of spectral fingerprint and PVC has a little bit different spectral fingerprint, we can now find the pixels from this image where actually this fingerprint exists. And then we paint all those pixels blue. And now the sorting machine, that sorting machine purpose is to separate different plastic materials to the different bags. And now the robot can do this based on this information. So the red items will be put to the red items box, and blue items will be put to the blue items box. So this way, by combining spectral measurement and imaging, we can do very efficient application for the sorting industry, and which actually works very reliable way. And it's not only like you can see here, actually all these wavelengths that we measure, they are beyond the range that our human eye can see. So we are not restricted. We started explanation of spectral imaging from color example that is actually visible for human eye. But with our sensors, we are not limited to that part of the electromagnetic radiation that is sensitive for our eye, but we can go beyond that for the much longer wavelengths that are not visible for the human eye, but which can what we can see with our sensors that actually reveals the chemical composition of the materials. And here, as an example, I will show you how easily you can actually create this type of algorithms that can sort different materials, because I can imagine that now you can think that, okay, this sounds very good, this looks very good, but I'm not a physicist, I'm not a chemistry expert, so how can I do this type of application by myself if I'm engineer or something else? So I will now show you shortly how to do this in high level. First of all, you need a teaching group of materials that you want to sort. Then you need to measure those spectral fingerprints with our SPECIM FX camera. With those measurements, you will create algorithm with our SPECIM Insight software. So SPECIM Insight will create algorithm that can sort out these different materials from each other. And Esko, after me, will show how to do that in practice. And after you have made that application with SPECIM Insight, then you can run that application in our real-time processing hardware, SPECIM Cube, real time on top of your production line. And then as an output, you will get RGB image with this sorting intelligence inside. So now if your algorithm, if your robot in your sorting machine find the red pixels, blue pixels, and green pixels, and then throw those items to the specific boxes, you have done this application. And our customers has create those models even in hours. So it's actually really easy to do with our SPECIM Insight, those algorithms. So I would say that this SPECIM1 concept, it follows our vision, spectral imaging made easy. And that's what we at the SPECIM would like to do. Because as you can imagine, there are a lot of different applications where you could use this spectral imaging. But we as a one company cannot do all that. So that's why we have made a platform that our customers can touch and create and find all those applications by themselves. And we will help our customers to be successful in their applications. And with, for example, this SPECIM1 concept, that is possible. So now we know the concept, what we mean with the spectral imaging, but how does that actually works in practice? What type of camera hyperspectral camera actually is? And our hyperspectral cameras are so-called push broom line scan cameras. So in this type of application where we measure reflectance from, for example, seeds here that are proceeding in the conveyor belt, we need, of course, line illumination light source, and then our camera here takes line images one after each other. So when the conveyor belt is moving like this, we take these line images, we stitch them together, and this way we form two-dimensional image. And every line here that has those spatial pixels, every spatial pixel has spectral measurement inside. And what is the benefit, or what type of special features you actually get with this type of approach? So the advantages of this push broom approach is that actually all the spectrum are measured at the same time. So there's no any need for any like a co-registration of images. The image is ready immediately after the measurement, and then you can immediately start analyzing your result. And that's very important in fast applications, because the decision what material this is, it has to become in fastest case in milliseconds. And there's no time for any image co-registrations or things like that. You have to immediately start analyzing your spectrum, and that you can do with push broom approach. So it's very straightforward data processing with this approach. In addition, another thing that is very important, is to get as good signal to noise ratio as possible in as short time as possible. And we can do that because we can use very high light collection efficiency lenses like f1.7 and at the same time still keep the very accurate spectral measurement. Let's say the spectral resolution can be 1 to 3 nanometers in best case. And that data we can collect with very high light collection efficiency lenses. And that is not possible with other technologies. Push-broom is the only one that can keep very accurate spectral measurement and have high light collection lens at the same time. Well, in addition, once you have made your first application, for example, with this FX10 that is sensitive for the visible range of the electromagnetic radiation, the same type of push-broom technology can be easily expanded to the other wavelengths as well, like SPECIM, middle wave infrared or long wave infrared ranges. So that way, I would say that this is the best technology that you can have for the hyperspectral imaging. And if you think about this measurement geometry, also the spectrum of the items is always measured with the same geometry. So it always illuminated similarly, because now, for example, if you think about this is moving like this, these seeds come to the measurement point, and the geometry is same for all the seeds. So now let's see here one video how actually this is working. So this is slow motion. So here you can see we measure the leaf, and immediately it creates the image, and every pixel has here the spectral information. And this camera can be used in very different type of applications. And actually in this image, you can see that there's during these years, over 25 years, what SPECIM has been in this market, there has been a very wide variation of different type of applications, starting of course from agriculture and vegetation, going to the color measurement, food safety, healthcare and pharma, geology, waste recycling, and environment. There are a lot of different applications that you can do with this technology. And let's see some of those at the end part of this this presentation. And now you may have understood that there is no only one camera that can be used for every applications, but actually there are different cameras for the different wavelength ranges and for the different type of applications. So IQ series, as you can see, it looks like normal compact camera. I will tell you a little bit more about that in the second slide. And then FX series has 3 different cameras. FX10 for this visible very near infrared range. Let's say here it says it's from 380 to 740, but actually FX10 goes to 1000 nanometers. Then we have FX17 from 900 to 1700, and SPECIM camera here is measured from 1000 to 2.5 microns, and FX50 for MView. And then AFX is for the drones, ISA is for the airborne, SISU is for the especially for the geological applications and maybe medicine inspection, and then just some other spectral cameras for different type of laboratory or conveyor belt purposes. So whenever you have any idea about the applications, just contact LINX, contact SPECIM, and we will help you to choose the right camera for your application. Depending, it might be we can recommend the right wavelength range and also the type of the camera that is suitable for your needs. And then I promised to tell you a couple of words more about IQ. So as you can see, it really looks like normal compact camera. It's easy to take to your backpack and go to the fields. And in this image, you can see that actually you don't need, when you use SPECIM IQ, that the technology inside the IQ is similar push-broom camera as in FX series. But the difference is now that the scanning function is actually made inside the camera. So when you use IQ, you can use it so that you just place your sample on the table, you put your IQ camera steering the samples, and then you push measure button and it will measure your samples and acquire the spectrum of that. And then we have IQ Studio, where you can then apply algorithms to make analysis for your data. And if that works, you can then put that application work in IQ camera itself. And then you can use this as a portable measurement device for a certain application to make this analysis directly in the camera. So this is very good starting instrument. If you are newcomer for the hyperspectral imaging and you could work within this wavelength range. So for example, you have some food or vegetation or similar type of application in mind, this IQ camera is very good starting product. And now we will go to the application examples. Well, we started with colors. So we will now also start this application examples with colors. So if you want to measure the color quality of, for example, some kind of displays or panels, you can do this with hyperspectral cameras, because actually we can measure spectral irradiance. And based on the spectral irradiance, we can then calculate, for example, LAB values of the color and ensure that the color quality in your display is good enough. You can see here, we can definitely calculate the color and represent that result in this type of chromatistic chart. Well, now here the example is the panel that is emitting the light, and then, well, this it's not only the color quality, but it's also how well this display actually emits, how uniformly that is emitting the light. It's not only the color quality, but it's also about the uniformity. And like in here, you can see that we can see the difference in luminance in different parts of the cell phone display. So both of these things we can measure, color quality and also the uniformity quality, because we take the image of the product. And then here it's not only panels but also LEDs that you can study with this. And when you take the image of the emitting LED, you can measure the horizontal profile. Let's say this is like a spatial profile with different wavelengths over the LED. Like you can see here, how the intensity is different with the different wavelengths, and also the shape is a little bit different. Or then you can go over the LED and measure the spectrum from center to the edge, like here. Like the spectrum at the center is this white. So when you measure from the center of the LED, spectrum looks like this. But when you go to the edge, you can see that it will change. So with hyperspectral imaging, you can study also LEDs very different ways. And then here I want to mention that even now we have a talk about these light emitting devices that we measure the color or spatial uniformity or things like that. But you can also measure the color from reflected light. So if you have a sheet of the paper where you have a different type of color box, let's say color rectangles, and you would like to define the color quality of that, you can do it also from the reflected light. So it's not, you don't need emitting product, you can use, or you can measure also this color quality from reflected light. Okay, but then totally different application compared to those what we have mentioned. You can, because hyperspectral imaging can differentiate between different materials, we can see here, for example, that if there is a part of meat at the wrong place, like here as a position of heat sealed packets, it means that actually this meat at the wrong place means a hole. That means that this is not anymore vacuumed. And that, of course, affects to the shelf life of this product and so on. So it's important that this type of quality checks can be done for this type of packages. So here, when this is good example that when you can combine spatial measurement together with spectral measurement, you can create totally new type of application because you can locate this wrong material at the wrong place. So yeah, so just use your imagination when you think about different applications where hyperspectral imaging can be used. And also here, interesting application which is not related to spectral fingerprints actually. This application is thin film thickness measurement, and it's based on the interference difference here when the light is first reflected from the thin film first surface, and when it's reflected also from the back surface. So based on the interference between these two reflections, we can actually define the thickness of thin film. And here you can see some numbers. So at FX10, you can measure thickness from 1.5 to 30 micrometers, and FX17 from 4 to 90 micrometers. Totally different applications that we have been thinking before, but it's possible also with spectral camera. Well, this is more like a, let's say, conventional hyperspectral imaging application if you need to define the minerals. So in this example, you can see the box where we have a drill course. And in mining, it's important to know where the valuable mineral, the ore, is located. And that should be do as fast as possible, because there's no time to waste when you are either looking for the location of the new mine, or then you are leading the production in the existing mine. It's very important to know where the ore is, so that you can lead the production, or then you can lead the survey process, so that this drilling is located to the right places. So we can actually measure 1 kilometer of this type of drill course in a day, and after that you can then analyze in what part the different minerals exists. Like here you can see that the red is kaolinite, and then quartz feldspar is located here with this color. So this is very powerful tool in mining industry. And in addition to this drill core measurement, you can also measure like a crust rock. So it doesn't have to be in this type of drill core. It can be also crushed. And when it's crushed, then you can create sorting application also for the mine industry, so that when these rocks are ongoing in the conveyor belt, the sorting machine can actually throw away the waste rock, and this way like increase the concentration of the ore in the input material to the beneficiary process. Yes. Okay, and then we go to the food applications. This here shows how you can use hyperspectral imaging for sorting nuts from the nut shells, and this works very well. So that there's a certain item in the nut that doesn't exist in the nut shells. And with hyperspectral imaging, we can see what parts has that certain material, it's oil, and what parts not. And based on that measurement, you can easily sort the nuts from the nut shells. And in this image, you can see how well it works. So these blue ones are the nut shells and the green ones are the nuts. And of course, then this is kind of, let's talk about like a foreign object detection. So like here you can see the stones in the fruit. For the human eye, it's not so easy to know where the stone is, but based on the spectral fingerprint, you can find that here is the stone of the fruit that is not wanted there. Or then about the quality of the fruits, like molds and bruises, you can easily see, like here with the human eye, not so easy to see, but with the spectral imaging, you can easily see those bruises and molds. And then about the meat. If you take a look about this image, for me at least, it looks like there's only meat and fat. But actually, with the hyperspectral imaging, you can see that yeah, there is a lot of meat, but there's also plastic somewhere. Like here, it's quite hard to see them. There's also a part of wood somewhere here. At least for me, it's very difficult to see them. But with the spectral analysis, you can see it easily them. This spectral imaging, now all these examples what I have shown to you, they are more or less so-called qualitative measurements, so that you can differentiate between materials, like in qualitative manner. But spectral imaging can be used also for quantitative measurements, as you can see here, like a meat grading. So you can define the amount of fat, for example, in your meat. So this we call quantitative measurement. And here, and the last image of this slide, you can see examples of the detection of concentration of spices. So if you go to the shop and you buy, for example, oregano, how much oregano is it 100% or is it 50%? If you take a picture of that with the spectral camera, you can define how much oregano there is actually in your bag. So this is important when we come to the food fraud applications, that you can know what you buy. Okay. One important thing in spectral imaging is to understand that mainly spectral imaging is surface measurement. So all the analysis is based on what you can measure from the surface of the object. But here actually, in this example, spectral imaging is used to measure interland defects in cucumber. And that is made by measuring also transmittance. So here is a transmittance illumination and also reflection illumination of the cucumber. And based on difference between those two measurements, you can actually find interland defects in cucumber. So in certain cases, it might be possible also to see inside your object, but typically it's a surface measurement. Another example here, what I want to mention, I don't have a slide about that, but I will tell you that if you want to see worms inside fish fillet, it's possible with spectral imaging. But in that case, you should illuminate the filler beside your imaging line. So actually you don't, if you want to see worm inside the fish fillet, you should not measure the reflectance from the surface, but you should actually measure how the light is penetrating to the fish fillet, and measure that light that goes inside the fillet and comes back. And that can be measured with the spectral imaging. We have applications where worms can be found this way. So if your application is related to fish, we have and you would like to see the worms, we know how to do it. And then let's think about ripeness of the fruits. Here is example how the spectrum differentiates, how the spectrum from the mango changes as a function of time. So from day 1 to day 19, because the ripeness level of the mango will change, that will also change the spectrum. And maybe that is more easily seen in this picture. Like a day 1, the spectrum of the mango looks like this, but as the ripeness level increases, also the spectrum changes. And like here, after 14 days, the spectrum is totally different. So with spectral imaging, you can define the ripeness of your fruits. And I think that for certain industries, this is quite interesting application. Well, now let's turn into the maybe a little bit more severe things like a disease or health of our food. In this example, there's maize kernels that are measured with our macro lens, and there's a fungal infection in certain kernels. And now when we compare the spectral fingerprints of not infected and infected kernels, they differ reasonably from each other. And based on this difference, we can again find what are the infected kernels and what are the healthy ones. Well, now the detection of disease is not restricted only to the laboratories. Here you can see examples of wheat related diseases, and those of course you can measure in the laboratory. If you go to the fields and you collect parts there and you go to the laboratory and measure there, that's possible. But actually, after you know what to measure, you can actually then go to the fields with IQ. So now this is example that if you first create algorithm that you with SPECIM IQ Studio that work in the laboratory, then you can put that application work inside your IQ camera, and then you go to the field with your IQ, and you can there take a pictures of the plants outside and immediately see if there is this disease or not. So yeah, just an example where IQ, for example, can be used very efficient way. And here more examples from tobacco, different type of disease. If you are more interested in that, here you can see the reference. And another disease from tobacco, again, here you can see the reference if you're interested in this. Some of our customers has been very interested in this tobacco disease detection. And all the examples that I showed to you before was examples in the laboratory or if you go walking to the field. And these cases, of course, the area you can measure is restricted. You cannot walk too much per one day or take the images. Also, it's quite time consuming to take a picture of one plant and go to another and so on. But here is an example that if you want to measure large areas, that can be done from the airborne. So similarly, as I showed to you that those diseases can be detected in the laboratory, you can actually do the similar kind of disease detection from the airplane. And in this example, there is this fungus disease in oil palm trees detected. So you just fly over your you just go to your oil palm plantations and you fly with your airplane large areas, and then you apply certain algorithms to your reflectance data for your maps that you have created after your flight, and then you can find this fungus disease. And it's not only, of course, oil palm trees. You can also go to the fields, find this disease from from weeds or tobaccos or so on. So it's very efficient tool if you want to cover large areas. Okay, that example that I showed to you in the previous slide, it was from the airborne, so with manned aircrafts. But of course, if you want, you can do this with the drones. And here is example with our SPECIM AFX camera used with the drone for certain precision agriculture application. So if you are familiar with the drone world, I believe you are familiar with different type of, let's say, multispectral cameras. So for example, with multispectral camera, you can define NDVI as we have done here. But now if you think about hyperspectral cameras is actually like 20 or 30 multispectral cameras in one device, because we can measure over 200 different spectral bands. So if you want, you can calculate this NDVI from the spectral data, but you can also calculate PRI or whatever vegetation index you have in mind. You have everything available if you have measured your fields with hyperspectral imaging. So once you have measured the field, you can generate all those vegetation indices in the world with this one data that you have measured. You don't have to measure with different cameras or whatever. It's just one measurement with hyperspectral camera and you have all the data available. And it's not only these vegetation indices that you can define. You can also find those diseases. You can find weeds. If there's like you would like to avoid some weed in your precision agriculture application, you can fly over the field, use certain algorithm and find those weeds from your field. So AFX is very powerful, very powerful camera also for drone application. And now when I mentioned to you about the weeds, here's example, certain type of, let's say, weed. It's not a weed, it's a marijuana plants. So this is of course law and enforcement related applications that if there's certain plant that you would like to find, like in this case, it's marijuana plants. This is illegal marijuana plant growing places. So when you fly over the forest and then you apply certain algorithms, you can actually let all the other items out and only marijuana plant plots are seen. And now, because this image is georeferenced, we know exactly the points in the map where these marijuana plants exists. So we know the coordinates. And this way, we know where other illegal plantations, or if you think about some other, like I was talking to you about the weeds, we know also the location of the weeds, and then we can go to the fields and take the weeds out. So example about how the spectral fingerprint can be used for differentiating different plants from each other. And this is actually my final slide. Also example about the application where detection of different plants is used. So in California, America, in USA, eucalyptus trees, they call them like invasive species there. And the reason why it's important to know where those eucalyptus trees exists is the problem with forest fires. So these eucalyptus trees are very easily, like they get burned very easily when they are dry. And for that reason, these eucalyptus trees, they form like fire channels where the fire can expand quite easily. So now when thinking about the evacuation or preventing the fire, if in case there is a forest fire, in order to prevent that to expand too much, it's important to know where these invasive target species exists, so that that can be taken into account in the preventing this fire expanding. For example, cut them out or whatever. So, well, this is my final example of hyperspectral imaging applications, but keep in mind that one slide where there's like tens of different type of applications shown. There are much more hyperspectral imaging applications that I have shown here, but I hope that these examples give you some ideas how hyperspectral imaging data can be used, and perhaps generates your own idea where this could be used, and we can then together think about what would be the certain the right product for you. So thank you for your attention. I will now pass this to S.E.A. and LINX Singapore. Thank you for your attention.
Thank you, Jussi. And thank you, LINX, for arranging this seminar. My presentation, which you should see now, concerns about how to make the actual measurement and how to make a qualitative application. I get a lot of questions how difficult it is to make an application. And my example here, which I'm going more detailed, is about how make a simple sorting application in practice. And I'm doing this with an FX camera. So the camera is FX17, working in the infrared region, so from 900 to 1700 nanometers. And the sample I have here is on the table. It consists of cotton, cardboard, polystyrene, and some nuts, nut shells, and so on. And because FX camera is push broom and line scanning, what we need to scan the samples. And I will show a video about that, and I'm starting it now. What happens first, the camera is measuring the dark image, and then we go to the white reference, which is at the end of the table, and then we measure our sample. So all the wavelength and all the spatial positions on this sample. And of course, in this case, we save the result to file so that we can open it in the inside software, which we are here using to make the actual application. What is our sample in this case? There are some fabrics, cardboard, and plastic. And at the lower part of the image, we have the nut and nut shell. And of course, we don't want to eat the nut shells. This is a color image, so standard RGB color image. And as you notice, the top samples have all their white in color. So in practice, looking or checking them with an RGB camera, you couldn't say or differentiate between the different materials. In the middle, you have polyester, cotton, and fleece, which have slightly different colors. But as you can see later in my presentation, this has no effect on the classification ability, mainly because we are not looking at the color, we are looking at the chemistry of these materials. And you can consider this application I'm making maybe looking for recycling or differentiating, sorting between different materials. You can also think this as looking contaminants in food or nuts. There might be, if you pick some nuts, maybe there are some plastic parts or cotton parts. Anyway, the sorting application that I am making is able to differentiate between all these different materials. The workflow that I'm following here is I have my sample starting from the left of the image. Then I made the data acquisition by scanning the sample. I do some pre-processing, and in this case, I will calculate reflectance from the results. So taking into account the white and dark, you can calculate the absolute reflectance, and that way subtract the instrument away from the measurement. But after this, we have the actual information extraction. What is there in the data? And we always start by looking the spectral region. So pixel by pixel, we have the spectrum, and using chemometrics tools, either qualitative or quantitative tools, we look what is the content of the spectrum and make the analysis and classification. And only after this, we start to look at the spatial things at the image. So using standard imaging analysis tools, some aerial analysis, or we can calculate histograms, or we can calculate different statistics from the image, but that's the second part. And finally, we want to show the result using visualization tools. Now, the final part is only for humans because we want to see what is there, but in industrial applications, after the spatial analysis, we might give a robot some commands, or the conveyor belt has sorting based on blowers or something, and then we just give command to these parts. And now we change to my software, which is our SPECIM Insight software. Now, I already input the sample or the image that I measured, and you can see it here on the right side. This is visualization from the infrared region. So we call this false color image. And you can see slightly different colors, but they are only changes in the infrared region. To make the application, we first need to train the materials. And we go to this training where we have our samples. And to make the training, we need a sample spectrum of each material we have on our image. We know these materials, so we can pick a sample. And I have a tool here, or actually several different kind of tools, but in this case, I can pick a square region from this material, and I can immediately see how the spectrum looks and what is at the variation. So the strong line here is the average, and then we have some aerial changes, mainly intensity changes on this spectrum. The second spectrum I pick is from this polystyrene. So I have two different spectra, one from cotton and one from polystyrene. And you can immediately see, looking from the lower part, the spectrum image, that those are totally different, which means that I may be lucky in this case to make the actual sorting based on this. Now I will name here these samples so that my first sample was cotton, and I give it to blue color. The second sample was polystyrene, and it's greenish color in this case. And before we go to pick other samples, I will also name the other classes I have in my sample. There was some cardboard, Second, there is this polyester. And of course, I can change the color for that using this software, but let's have those colors that. Then we have these. There I might take a little bit different color, maybe yellow for this material. And then finally we have nut and nut shell. And after we have named all the materials and given them right suitable colors, I will pick. So this was cotton and this was polystyrene. The same way, I will pick samples from each material I have here. Like this. And then I will pick them here. And I have nut and nut shell. Now when I have taken only a small sample or a spectral sample from each surface here, I can test how well the model based on these areas actually work for the whole full image. And there I can use the test button. Now it calculates the model based on these test surfaces and shows how well this works for the full image. And we can immediately see that it's actually quite nice. We had two cotton samples, they are blue. Then we have this cardboard polystyrene, and the full area is actually now colored with the right color. There are maybe some problems in my nut sample. So there are small places where the nut is actually classified as nut shell. And I am able to try to make this slightly better. And usually I try some pre-processing tools. And in this case, I use Savitzky-Golay smoothing, and I hope that this would improve my classification. I can select some parameters, and then I can test whether or not this improves those small defects I have in my classification. This sometimes works, sometimes it does not give better result. But anyway, it's one way of improving the sorting algorithm. And now we can compare the results. So we have two different results. And in my opinion, the Savitzky-Golay smoothing slightly improved my model. And this model can now be exported and used for sorting these materials in online application. And as Jussi mentioned, we have this SPECIM cube computer where we can export this and immediately start using this model. It took me about maybe 15 minutes to make this application. And as you can see, we can have many different organic, inorganic materials, starting from paper to cotton to different kind of textiles, different kind of food materials, and so on, and quickly make a qualitative application, so sorting application, finding contaminants, and so on. If you want to make a quantitative application, for example, we have a textile containing cotton and polyester, like many men's shirts have. That's a quantitative application. We want to know what is the percentage of polyester in the shirt and how much cotton we have. Then you need to make more work and you need more measurements to make this, but it is possible. I hope this made it clear that it is actually quite simple using the software tools to make a application and test how the application works. We do have the possibility to make a second measurement and validate with the new samples, quantitatively validate how well my model works in these cases. And that takes, again, the next 15 minutes. But as a quick, simple explanation, this is enough in this stage. So that's all I have at the moment, and I leave my presentation. So LINX Singapore, please continue. I think it's the time for questions.
Yes. Thank you, S.E.A. and ESCO. It's a very interesting and informational presentation. We hope you all have learned something today. So we are now open for Q&A session. So please do type in your questions so that ESCO and S.E.A. can, we'll try to answer all of them within the time frame. For those questions that we are unable to answer them during this session, our team will keep in touch with you and after this. So we shall start with the first question now. Okay, there's one question from Martin. Can it detect particle and fiber on hard disk drive, media up to 0.1 size? Particle material like talc, metallic, fingerprint oil, plastics, and glass.
Typically, metals are rather difficult. So because there are surface reflection and this light doesn't penetrate the metal, and it's the metals you should know case by case which are able to measure and which are not. But other materials like oil on the surface, contaminants on the metal surface, and so on, those are possible.
Okay, so let's go to the next question from Hui Ying. Give me a second. Okay, she was asking, she's curious to know if there are any database available that could help with identifying unknown samples based on their spectrum.
At the moment, I know only few databases, and they are mainly for mining industry, so geological databases. Because the database is actually rather quickly made. Like I showed here, I have now a database in my computer to sort different polyester from polystyrene, cotton, and cardboard. If you have limited amount of samples, say 5 to maybe less than 100, the making of this kind of library is really, really simple and quick. And so that's not the limitation. However, if you have totally unknown material and you need to know, and there is a possibility of maybe hundreds of thousands of different chemicals or constituents in that material, then you must have a library. And the only one I know is the database for geological applications. So in general, there aren't, but in some specific cases, yes.
And if I follow a bit here, there are a lot of different articles made with hyperspectral imaging. So it's not like a collected database, but if you study the different articles, there are shown different spectrum, different materials in those articles. So if you go to the article database, you may find your spectrum there.
Okay.
One thing more. if we take the application where you want to see and select contaminants out of, for example, nuts, you only want to pick the nuts, then the only library you need is to know what is the spectrum of nut, because others are actually foreign materials and they are actually then contaminants. You don't need to measure hundreds and hundreds of different materials to pick only nuts out of your conveyor belt. So you have to remember that there are usually, in industrial cases, there are a limited number of materials that need to be detected.
Okay, let's move to the next question. What is the field of view for SPECIM FX cameras?
We have different possibilities because the FX camera, we can change the Fourier optics. So depending on the application, we can change it. So there are wide field of views and then a lower field of views. So the standard one is 38 degrees field of view, but then I think the lowest one is, Jussi, do you remember 14 degrees? And then the widest.
I don't remember what was the what that was in degrees, but if I remember correctly, we can use macro lens with FX17, and then I think it's like was it even 1 centimeter or something like? But it's we get very good spatial resolution with macro lens, even like 40 micrometers or so.
Yeah. So there are different possibilities, and because we can also use C-mount in FX camera, you can actually pick any C-mount lens from any third-party supplier, as long as the wavelength matches the camera wavelength range. So with the FX10, the lens must be designed for 400 to 1000 nanometers, and for FX17, you have to buy a lens that matches 900 to 1700 nanometers. But you are not, the SPECIM lenses are not the only ones here. You can use any third-party lens as long as it has these limitations.
Okay, the next question we have here is, can we find the abscess in the pork meat by determining from the condition of the meat?
This is there are few cases for meat, for example, where you can actually do the application, and in most cases we want to test it first. We know that there are a lot of applications for testing the contaminants in meat, the aging of meat. So, but it depends slightly on the customer needs. So I would urge the customer in this case to contact us, and we can talk more about these applications. But in general, there are a lot of possibilities.
Okay.
Yeah, well, yeah, well, if I a little bit continue it, so that if the abscess is visible, I believe it's definitely can be like detected. But in case it's not visible, then we have to do as Esko said, that we have to study if the condition of the meat changes, so that we can see, for example, the abscess inside the meat and so on.
Okay, I think we have time for another 2 more questions. So the next question is, in training example, if we train the model with the pure materials, can we differentiate materials if they are stacked on each other like multiple layer samples?
Yes and no. This again slightly depends on the case. So if the material is not transparent, then of course the underlying materials cannot be detected. But for example, if Jussi showed the example where we have a chicken packed in a plastic container, and we can actually see the plastic, but we can also see the chicken inside. Plastics are typically slightly transparent, and in these cases, we can see the possible contaminants inside the bag. The general rule is that this is surface measurement, but in some cases, we can also see what is inside. As a medical application, we have these blister packages where you have packed your pills inside a plastic. Then can you see what is inside? And my answer is yes. You can actually see through a thin layer of plastic, and you can determine in a blister package what medicine is inside and is it the correct one. Again, this is slightly case by case, so we urge customer to contact us and we can negotiate and even make some tests.
Okay, maybe we can have one last question here. So from Cheng Yin, we have, given we can identify objects, say nuts, nutshells, apples, and grapes, etc., using different wavelengths or spectrum, how does system integrator design the pick and place on conveyor belts, for example?
Can you just answer this question?
Could you repeat the question so that I can think a little bit more in detail?
Okay, I repeat the question. Given we can identify objects like nuts, nutshells, apples, and grapes, using different wavelengths or spectrum, how does system integrator design the pick and place on conveyor belts?
Okay, yeah, now I understand. So in case they use SPECIM cube, the output is RGB image. So they define that this red color is, for example, for the apples, and blue color is, for example, I don't remember anymore those examples in your question, but let's say it's like a plastic. So now this robot will know that when there comes this image stream, so those blue pixels, the pixels that are marked as blue, they belongs to the apple, and then these red pixels goes to the plastic. Oh, I don't remember anymore which way these colors means, but the idea is this, that they are coded by the different colors in the pixels. So it's then very easy. It's kind of, I would say that this SPECIM one concept transforms hyperspectral camera as a normal RGB camera, but it has this intelligence inside to separate different objects. But output is RGB image.
Okay, so thank you. Thank you everyone for your participation in this Q&A. So we are sure that you're excited to explore more about the hyperspectral cameras. So for more information or for a demonstration, do not hesitate to contact us or call us at 6842-0500. So in our next segment, our regional sales manager, Chung, will be sharing a summary of today's topic. Please join us, Chung.
Hi, very good afternoon to everybody. I hope you enjoyed the presentation. Many thanks to S.E.A and UC for the wonderful hyperspectral presentation today. Right now, we would like to also introduce to you that LINX Singapore, we have the SPECIM IQ, which is a portable camera, right? It looks like a DSLR, as well as the FX10. All right, this is the physical side of it. As well as we have the lab scanner, which is attached. You can do the line scan applications to it. Okay, so if you have any applications that you have thought about or probably could work with hyperspectral, yes, please contact us. We have offices in Malaysia, Singapore, and as well as Thailand. Okay, and you can contact us by emailing us, and our email can be found on our website. So with that, I'd like to thank everybody for their participation today, and I'll hand over to Mrs. Cecilia right now. Thanks.
Thank you, and bye.
Thank you. Thank you, Sean, and all our presenters. Just for info, for local organizations and SME in Singapore, if you're interested in our products, and we can actually assist you to work on relevant government grant as well. So do contact us for more information. So with this, we have come to the end of our last series of LINXDays Southeast Asia 2021. For all the attendees today, you will be receiving a follow-up email from us after this webinar. So if you have any other questions, you may reply us via email or send to us on our sales email. So thank you once again for being here with us. We truly appreciate your participation. So stay safe, take care, and we will see you in 2022. Bye.
Bye.